All right, so your last new topic for the year is something that we refer to as a binomial expansion theorem. And what we're going to start with to lead into this is a little triangular array that's known as Pascal's triangle that kind of gives you a little shortcut to finding some of these expansions. Now, I copied your notes sideways on purpose. Let me show you some of these problems, and I'm just going to warn you because I write large too. So your problems get very lengthy, like this direction. So same thing when you go to do your textbook homework, if you want to take your notebook and turn it, then you can kind of fit these a little bit better. So I'm just showing you that for planning purposes so you kind of make sure you can fit everything across your paper. So what the binomial expansion theorem is a method for expanding binomials. So binomial is like this. So it's like your FOILing process, like A plus B. Okay? And what you will find, I'll have you do just a couple of these to start, is there are going to be numerical patterns that emerge when you expand these powers out. Okay? So I'm going to start at the first one, show you where these come from. So if I have a plus b raised to the 0 power, you have learned anything to the 0 power is just 1. So the next expansion, if I do just a plus b, it's obviously a plus b. Third line down, if I take a plus b and I square it. And again, you've done these a million times before. So take the binomials, multiply this out. And again, what you're looking for today are emerging patterns. So a times a is a squared plus a times b, write it alphabetically, a times b again, and plus b squared. So from the past, obviously, you know to combine these, and I get 2 copies of ab and plus b squared. Okay, so that's just your binomial squared. Again, you've done that before. So if you have to take that answer and cube, so 4th line down, I would then take a plus b and distribute it through my resulting answer, which was a squared plus 2ab plus b squared. And again, this is just the background to show you where this comes from. So I would distribute this. A times a squared is a cubed. And then a times 2ab would give me 2, and I like to write these alphabetically, a squared b. A times b squared would be ab squared. And then plus b times a squared. I recommend writing it as a squared b. B times 2ab would be 2ab squared. And lastly, b times b squared is b cubed. And again, you're trying to draw your eye to a particular pattern with this. So if I combine like terms, I have a cubed plus, I have like terms here and here for a total of 3a squared b. I have like terms here and here for a total of 3ab squared and ending with b cubed. Okay, you guys see how the 3's are both inside there? So it goes 1, 3, 3, 1. So again, another pattern. I won't make you multiply out your 4th power, but I just want you to look at it. So if I took a plus b to the 4th power, I would essentially have to take this answer times another a plus b, which is very time consuming. I would combine like terms, and I would get this line right here. And if you look closely at it, what happens is I start with a power of 4 on A, and you'll see it decreases by 1 for each consecutive term. Then your B value starts at 0 because it's not there. Power of 1, power of 2, power of 3, power of 4. So what you'll notice today is that your first exponent is going to decrease. So your first exponent will decrease all the way until it hits 0. And your second exponent is going to increase. The second exponent will increase. So if you take those binomials and their expansions from above and you pull off all of the coefficients, what you're going to get is this triangular array. Do you guys see how there's ones all the way on the side? And then you see the pattern right here, 1, 2, 3, 4, 5. And then it repeats kind of in the center like that. It has the symmetry. So this is what we refer to as Pascal's triangle. So it's essentially a shortcut and a time saver to expand binomials. So I'm going to show you one expansion with Pascal's triangle, and then I'm going to show you the binomial expansion formula theorem. And ultimately what you're going to want to do is use the formula, because this is something you would have to memorize if you ever wanted to use it. Okay, and there's no point in memorizing that. So your first example says to use Pascal's triangle to expand. So I have m plus 3 to the 4th power. So I'm going to look up here to the 4th power, and I am going to grab this expansion right here and put my m plus 4 into this formula. So I take this line right here and use it down here. So I'm going to write it out first. So this is going to be equal to, so we're going to have a to the 4th and plus 4a to the 3rd b plus 6a squared b squared plus 4ab to the 3rd plus b to the 4th. Okay, so again, this is much faster than if I had you FOIL this out 4 times. So m represents the letter A and 3 represents the letter B. And I substitute these in now. So I'm going to get m to the 4th instead, plus 4. And for a to the 3rd, I just replace that with m to the 3rd. And for b, I replace it with 3. Plus 6. And for a squared, I replace it with m squared. And for b, I'm going to replace it with 3. And we're going to square it. Plus 4. A is m. And b is a 3. And we're going to cube it. Plus 3 to the 4th. You guys see how that works? And again, it's faster than FOILing, I promise. So now you just multiply this out and then you're done. So I get m to the 4th plus 12m to the 3rd. Answer is always in standard form. 3 squared is 9. Multiplied by 6 is 54. M squared plus 3 cubed is 27. 27 times 4 is 108m. And 3 to the 4th power is 81, and you are done. So again, it's a little shortcut. What you want to observe from this too, because it will make it easier when we get to your theorem, is that your first exponent is always going to decrease, and my second exponent is going to increase. And again, until they flip-flop at the end right there. Good so far? Okay, so what we do give you on tests and final exams is this formula. This formula is nothing you ever have to memorize. So this is given on formula sheet for your final exam. It's very easy to use, and it has all the same patterns that you just noticed with Pascal's. Now, this uses a probability notation that's known as a combination. And again, I have a feeling just like the factorial, you probably haven't seen this in the past. So when you see NC0, that is pronounced as N choose 0. This can be calculated right through your math menu on your calculator. So we'll go through that. So on the calculator, you're going to hit math, and you are going to go over to probability, and you are going to select number, I believe it's number 4, and it'll say NCR on it. What those combinations also coincide with is these are also the coefficients from Pascal's triangle. So if you didn't want to use the calculator to get them all, you could refer back to your notes as well. All right, so let's jump in and start one of these expansions. Again, I'm going to caution you with this one. The larger the power, the bigger physical space this is going to consume on your paper. So in expansion with a power of 6, this is going to be long, okay? So just write a little small, start to the left of your paper. So how this works is I take my exponent and I do 6, choose 0. So that's from my formula. It says n choose 0. And then what I do is this value of n always becomes your first exponent. So I take the x and I raise it to the 6th. And then I take my second, which is the y, and I raise it to the 0. Your exponents will always add to the front value. So exponents always add to the front number. In this case is 6. So always add to your front number. Okay. Now I do the next term. So this is where I apply the pattern. So the formula will tell you as well. So the formula says now do n minus 1. So I do 6, choose 1. My first exponent decreases to 5, and my second exponent increases to 1. So again, this one goes down, this one goes up. Plus 6, choose 2, x to the 4th, and y to the 2nd. Plus 6, choose 3, and this is x to the 3rd, and y to the 3rd as well. You guys see the pattern? Okay, and then plus 6, choose 4, and I go x to the 2nd and y to the 4th. Almost done. Plus 6, choose 5, x to the power of 1 and y to the power of 5. Lastly, 6, choose 6, x to the 0 and y to the 6th. And what you will notice is that last term, the exponents in comparison to the first term have flipped. So now you're good. So now what we're going to do is we're going to get all those combinations from the front. So I'm going to show you how to do that on the calculator. So I'm going to type a couple of these at once. So that one we need, that one we need, all of these. And this is going to resemble the same pattern from Pascal's triangle. So in the calculator, you are going to hit the math key and you're going to scroll over to where it says probability. And you're going to select choice 3. I'm sorry, I think in your notes I wrote 4, but I think it's actually 3. And you're going to type in, our first one was 6, choose 0. And then you hit enter. And now you do it again. So math, over to probability, choice 3, 6, 6, choose 1. Enter. And then do it again. So you're going to go math, over to probability, and we're going to go 6, choose 2 equal to 15. I'm going to do one more, and then I have a pattern here that's emerged. So 3, so I have 6C3, and then it goes back down from there. So my coefficients in the front are going to be 1, 6, 15, 20, and then 15, 6, and 1. And what you notice is if you compare that right here, actually I didn't take that one that far, but if you took this one more step, you would have seen that pattern emerge from Pascal's. All right, so our combinations were 1 and I forgot, was it 6? 6, thank you, and then it was 15, right? And then 20, and then 15, and then 6, and then 1. Okay. Now I do all the variables. X to the 6th is just going to remain x to the 6th. Y to the 0 is just 1. So there's the first term. We'll clean that up in a second. Next, this just becomes x to the 5th y. So that one, there's nothing you have to do with. Same thing. There's nothing I have to distribute on this one either. Next one, x cubed, y to the 3rd. Nothing I have to do special to that one. This gives me x squared y to the 4th. This gives me xy to the 5th. And then lastly, x to the 0 gets replaced with a 1 instead. And then y to the 6th. So here's your answer. So answer for this full expansion is x to the 6th plus 6x to the 5th y plus 15 x to the 4th y squared plus 20 x to the 3rd y to the 3rd plus 15 x to the 2nd y to the 4th plus 6xy to the 5th and ending with y to the 6th. Okay, so that is an expansion to the 6th power, which is quite lengthy. Typically, we don't have you guys go beyond that, okay? Because obviously, if I gave you one to like the 11th power, it's the same procedure, but it's just a little bit unnecessary to do. All right, so letter B, is it going to be shorter or longer? Shorter, way shorter. So again, keep that in mind too for physical spacing on your paper. This is only an expansion with a power of 3, so smaller. So my full expansion goes, I start with 3, choose 0. 2x gets raised to the 3rd. And be careful, use the negative y. And that gets raised to the 0. So these exponents need to add to 3 this time. Plus 3, choose 1. 2x to the 2nd and negative y to the 1st. Plus 3, choose 2. 2x to the 1st, negative y to the 2nd. And lastly, 3, choose 3, 2x to the 0, and negative y to the 3rd. Now, the 3rd power is in Pascal's on the front of your notes, so I'm actually going to speed this up and flip over and grab all of these coefficients instead of using the calculator. So if I flip, I'm looking for my exponent of 3. So exponent of 3 means my coefficients are right here, 1, 3, 3, 1. So you're welcome to use that just to save yourself some time. So this was 1, 3, 3, 1. Now you're going to do your x's and y's. So what makes this one a little different is that first term, when I have 2x quantity cubed, I need to cube the 2 as well. So this is really going to become 8x cubed, and anything to the 0 power is 1. Next term, 2 squared is 4, and then x squared. Next term is just negative y. 2x to the first is just 2x to the first. A negative raised to an even power is positive y squared. Last, 2x to the 0 power is just 1, and a negative raised to an odd power remains negative. So then you just put this together. So I have an answer of 8x cubed. 3 times 4 is 12 times negative 1 makes this negative 12 x squared y plus 6xy squared minus y cubed. Okay, so that is an expansion power of 3. How's that? Do you guys see the pattern? Good. So your last 3 examples are cases where you don't have to do a full expansion. Instead, what the questions ask you is just find a specific term. So for this one, like if you just wanted the second term, this would be the only setup that you actually needed. So we'll do a couple of those and then that's it. That's all you have to do with your theorem. So I only need the 4th term for this example. So what I recommend you do so you don't need to memorize anything is we just write out the combinations to figure out what is the setup going to be. So I have an exponent of 5. That means that my first term would start as 5 choose 0. We don't want that one though. I want the 4th term. So my next term would start with 5 choose 1. Don't want that one. The next term would be 5 choose 2. That's the 3rd term. In the 4th term is going to start with 5 choose 3. So that is the setup I'm going to use. So you're going to take your first expression here, so the 2x, just that part. And the rule is I'm going to raise it to the front number minus the back. Just like what you did on the other side, these powers have to add to 5. So currently, this is just going to be a 2. So my next expression here, the negative 3y, is essentially raised to 5 minus that answer. Again, which is just saying 5 minus 2. So I continue, clean this up a little bit. So I have 5 choose 3. I have 2x raised to the second, and then negative 3y raised. So 5 minus 2 would be power of 3. Okay, so those still add to the front just like you saw before. Next, you can either use the calculator or you can go back to Pascal's. It's up to you. I think the 5th was the last one you have written in your notes. I don't think I went any further than that. I would probably just tell you do the calculator. So 5 choose 3 and the calculator is just 10. And then you're going to take this and distribute. So I get 4x squared. And then my second one, I'm going to do negative 3 to the 3rd, which is negative 27. And then y to the 3rd. Then you're going to grab your calculator and multiply this out. So I need here a 40 times negative 27. So my answer is negative 1080 x to the second, y to the 3rd. And that represents the 4th term of my expansion. Okay. So I'm going to give you just 2 more of that type, but you don't need to do the full expansion for those. You can shortcut it just like that to find the particular term you're looking for. All right, so we'll do another. So find the 4th term for this expansion, and this starts with a power of 5. So my first term would be 5, choose 0. I don't want that one. 5, choose 1 comes next. Don't want that one. 5, choose 2. Don't want that one either. So 5, choose 3 is again your setup. So I go 5, choose 3. I take the negative 2x and I raise it to the 5 minus 3. And then I take my y and I raise it to 5 minus that result. And then you're going to just, again, use your calculator for the combinations. So 5, choose 3 is 10 again. The next term would be negative 2x raised to the 2nd power, and then y raised to the 3rd power. Okay. So now I need to distribute my squared. So I have 10. Negative 2 squared, so I have a 4x squared from the middle, and then y to the 3rd. So your resulting 4th term is 40 x squared y cubed. And they're not bad, they're very pattern based. So number 4, here's your last one. Find just the 6th term of this expansion to the 11th power. So here are my setups again. And again, if you're kind of catching on to patterns too, you could probably leave that part off. So I would begin 11, choose 0. That's my first term. 11, choose 1, second term. 11, choose 2, third term. 11, choose 3 is my 4th. 11, choose 4 is my 5th, which means 11, choose 5 is what I need here. If you've noticed as well, my second number is always 1 less than the term I'm looking to find. So you could use that as a shortcut as well. So 11, choose 5. I take the 3x and I raise it to the 11 minus 5. And I take the negative 2y, don't forget the negative, and I raise it to 11 minus that answer. So 11, choose 5 is in your calculator. So that is equivalent to 11, choose 5, 462. 3x raised to the 6th power and negative 2y raised to the 5th. Again, those are always going to add to your front value of 11 in this case. So I keep going. I get 462. 3 raised to the 6th power is equivalent to 729. X to the 6th. Negative 2 to the 5th is negative 32. Y to the 5th. All right, so last, I need to take the 462, multiply by 729 and negative 32. And I get a leading coefficient here equal to, let's see, how many sevens? 1, 2, 3 sevens, 536, x to the 6th, and y to the 5th. So I have comma and comma, negative 10 million, give or take. Okay. Are there questions on finding the specific term or the full-on expansions? Okay, very reasonable, right? So with your remaining time, You are welcome to start. Let's find it here. Any of these homework assignments, if you'd like, if you need to get organized, that's fine too. So for this week, you have a textbook assignment with binomial expansion theorem. Again, feel free to turn your paper sideways so that you can better fit those. You have a delta homework, and then you do have a test as well. Tomorrow in class, we'll review for your test. Homework assignments, I'm giving you, again, a lot of flexibility and extra time on that. Homework assignments, I'm not checking those till next Thursday in class. In your delta test, you can have until Sunday, the 16th, if you need it, until midnight to get those completed. And just as a heads up, because of next week's AP testing, on Wednesday will be your work day that you're welcome to work on any of those. And then the other 2 days, we'll kind of do some final exam review instead.